All right, welcome back from spring break. I hope you had a good one. So I'm guessing a lot of you went to the sea, to an island in the sea. Maybe you went on a boat, and here you are with your little pashmina. Yeah. Hi everyone. And whatever. So that's you with your little pashmina on a boat, and now we come back to reality, which is kind of 2K2 world. Believe it or not, somebody wrote this on a 2K2 test 2, and I just have a bad sense of humor, so I just thought it was funny. I think the student did it on purpose because they knew my humor, but yeah, play too many video games, and this just messes with your head. So game over, happy face with too little. That's why video games are bad. They mess with your humor and they mess with your head. Anyway, so yeah, so that's the transition from vacation mode, and now we're getting back into our 2K2 world, and hopefully we can go from this to this in the next few weeks. Yeah. So on that note, so we've already gone over test 1, test 2. The average for test 2 was quite high. You can look it up online. It was in the 60s. I think it was mid 60s or maybe a little higher than mid 60s. I don't actually remember. I've also been on spring break mode. Here, here's my pashmina from being on a boat. Anyway, so yeah, exam grades were good. There's a couple of you I'm concerned about. I haven't really contacted anyone, but I know some of you are not doing well that are coming to class. I would highly recommend that you ask for help. You can still turn things around in the next few weeks. Uh, as you know, to pass this class, you need roughly a 50% average on the exams, and you need to basically get a perfect on the homeworks, and then on the quizzes, I think it's like 70%. So if you are not anywhere near there, please ask for help. You can still catch up. Hopefully all of you will pass this class and then move on to the next ECE adventure. But yeah, if you're having problems, you need to ask for help, whether it's me, whether it's Piazza, whether it's your colleagues. Ask for help. Yeah, so I'm done with my infomercial mode. Now let's get started with lecture. So just as a reminder, in the last few lectures before spring break, we defined this so-called Laplace transform, which basically goes from a function of t to a function of s. And then we also found a way to apply the inverse Laplace transform, which allows us to go from an f of s to an f of t. And so far you should have been like, okay, yeah, sure, I can basically take a function and I can define its Laplace transform f of s as the integral from 0 to infinity of f of t e to the negative st dt. And I can define this f of s, but so what? Like, what can I do with this? Well, what we will do today is actually define a way to write our circuits in the Laplace domain so that we can solve them in a way so that we can treat capacitors and inductors in the same way that we actually treated resistor networks. And so that's going to allow us to basically very easily apply KVL and KCL in the Laplace domain while avoiding all these differential equations, and then just do an inverse Laplace transform to solve for the dynamics of the circuit. The next I think the next 3 lectures will focus mostly on using Laplace techniques to solve circuits. And then after that, we will actually kind of get into a more meta level where we will actually start looking at the Laplace transform of the impulse response and start to derive properties of the circuit from just looking at the Laplace transform. And that's ultimately what we want to do as engineers. We want to kind of extract global features of the circuits, and that's why Laplace techniques will be much more important going forward. But before we can start looking at kind of the global properties of circuits, we're going to start by looking at how to solve circuits using Laplace transforms. So we got to kind of build up step by step. Okay, yeah, so let's get started with our class. So in particular, we're going to be using this part of Laplace transforms, this property of Laplace transform, which is mainly that it's you can actually, it's a linear transformation. So what does it mean to be a linear transformation? If I take the Laplace transform of this, which is just a constant times f of t plus a constant times g of t, that's equal to the Laplace transform of f of t times that constant a plus the Laplace transform of g of t times that constant b. So we're going to be using this today. Now to prove this is actually very straightforward because remember that you can always pull out constants out of integration, and you can always separate 2 added quantities when you do integration. So effectively, you can write this integral here as 2 integrals, one with f of t and the a outside, and one with g of t and the b outside. And of course, this is actually by definition the Laplace transform of f of t. And this is the Laplace transform of g of t. Sometimes we don't even write it like this. We just say f of s, or g of s, in this case, g of s, and f of s. I like to write the L sometimes because it's kind of more clear that it's a transformation of f of t. Okay, so we're going to be using this today, the fact that the Laplace transform is linear, and in particular what we're going to do is we're going to look at what happens to KCL and KVL under the transformation of a Laplace transform. Okay, so in particular, when we do KVL and KCL, if we were to apply KVL on a loop, so remember, I could have a capacitor, I could have an inductor, so this is R1, R2, C1, L2. So if I were to look at the voltage drop around this loop, it would be kind of VR1 plus VR2 plus VC1 plus VL1. And that should all be equal to 0. So the voltage drop across each of the elements, so this could be minus, plus, minus, plus, minus, plus, minus, plus, should sum up to 0. So basically, if you look at the sum of the voltages, that's KVL. Now, if I write this in the Laplace domain, I could take the Laplace transform of this whole thing, and I'm just going to get that the sum of voltages in time is equal to the sum of the Laplace transforms. So of course, this is all a function of time time, time, time. When I take the Laplace transform of this equation, I'm just going to get V R1 sub S plus V R2 sub S plus V C1 sub S plus V L sub S equals 0. So what that means is that KVL holds in the Laplace domain. And additionally, a similar argument would allow us to say that KCL also holds in the Laplace domain. So basically, if I have a node and then I have a number of elements connected to this node, so I have IC, IR, I could have an IL, IL, could have another IR, I could have a I source, whatever, it doesn't really matter. Now we know that the sum of all these currents has to be equal to 0. Well, by the same argument, we can move the Laplace transform into the inside, and we're going to get that the sum of the Laplace transform of the currents has to be equal to 0. So what that means is that if I draw the circuit in the Laplace domain and represent each of the currents in the Laplace domain, they will still follow KVL and KCL. Okay, well, how do we actually represent a circuit in the Laplace domain? Well, to do that, we have to look at the IV relations and take their Laplace transform. So for a resistor, we have that V sub t equals I sub t times the resistance. Well, that means that V sub s equals I sub s times R. Now for the capacitor, I sub t equals C dV dt. So that means that I sub s equals C times S V sub s minus V sub 0. So remember the differentiation property of the Laplace transform. And then for the inductor, we can do the same thing using the differentiation property to say that V sub s equals L I sub s minus I sub 0. So we can take the Laplace transform of a circuit, IV relationships, and then now what we can do is define elements in the Laplace domain for capacitances and inductances. And now we can actually derive equations in the Laplace domain. So how are we going to do that? Okay, so in particular for this lecture, we're going to assume, so for this half of the lecture, we're going to assume that the initial conditions are 0, which means that we no longer have to subtract I sub 0 or V sub 0 when we apply this relation, or is this V sub 0? Yeah. Or actually V sub s, SC, yeah, V sub 0 times C. And we don't have to actually do L times I sub 0. We don't need to subtract that from the V sub s because we're assuming 0 initial conditions, and that's what we're going to call the 0 state response. Okay, so when we assume that all initial conditions are 0, the IV relationships for the resistor, which is V equals I times R, kind of follow this relationship. The capacitor, which has a relationship that I equals d dt of V times C, now we'll have that I equals SC times V sub s. And we can write this as V sub s equals I sub s times 1 over SC. And then for the inductor, we have that V equals L d dt of I, which basically translates to, in the Laplace domain, V sub s equals I sub s times S sub s. Now, we can generalize this concept of the resistance into what we're going to call the impedance. So the impedance of a resistor is just going to be R. The impedance of a capacitor is just 1 over SC. and the impedance of an inductor is just ZL. And then we're going to have that in these three cases, the voltage of S will be equal to the impedance of S times I's of S. So now, algebraically, in the Laplace domain, resistors, capacitors, and inductors behave the same way. And so analyzing a circuit in the Laplace domain will be the same as you would resistor networks in the time domain. So what do I mean by that? So for example, if I were to look at this circuit here in the time domain, to derive a differential equation, I would have to say that Vn equals the voltage across the resistor plus the voltage across the capacitor. And the voltage across the resistor is just I times R. And the voltage across the capacitor is just VCs of t. And then I would apply my IV relations for the capacitor, and then I could get my differential equation. In the Laplace domain, the resistance gets replaced with an impedance of R, and the capacitor gets replaced with an impedance of 1 over SC. And to derive the equation for the circuit in terms of VC, we could do voltage division, or we could just say that Vn equals ZR times I sub S plus CZ times I of S. And then once we have this, if we want to write this in terms of VCs of t, we have to realize that I sub S is equal to V sub S is equal to VC sub S divided by CCs of S. And so I can just rewrite this as Vn equals CR over CC sub S, and so I sub S plus VC sub S. And that's exactly the equation I have here in this line. And now I can just plug in for C sub R is just R, and this is just 1 over SC. So I get this. Now, if you look at this, this is actually corresponds, if I were to take the inverse Laplace of this, it would just be RC times ddt VC sub t. And if I inverse Laplace this, then it's just VC sub t. So I get the same equation out, but algebraically I can deal with the circuit now as if it was a resistor network. At this point, we've assumed zero initial conditions. In the second half of this lecture, we will assume non-zero initial conditions. So let's look at another example. So let's say we want to analyze this circuit. So we can take the Laplace transform of each element. So we're going to get that this Vn, if we use this table, e to the negative 3t u of t is just 1 over s plus 3. This is plus minus, plus minus. And then we have here, this is just S times L, which is just 0.4 S. So that's ZL. And then we have a CC, which is 1 over, C is milli, so 1, 2, and 3. So there should be a 0 and then a point, 0.05 S farads. Well, actually, it's impedance, so 0.05. Okay, so we found Vn sub S. So now we can actually find what IL sub S is. Well, ILs of S is just equal to VNs of S divided by ZL plus CC, which is just equal to 1 over S plus 3 divided by 0.4 S plus 1 over 0.05 S. And there you go. That's it. We found the equation for ILs of S in terms of VNs of S. Of course, we can clean this up by multiplying both the top and the bottom by S over 0.4, S over 0.4, so that we get that this is actually equal to S over 0.4. Yeah, so S over 0.4 which is 10 over 4. 10 over 4 is 2.5. So 1 over 0.4 is 2.5. That's where I get that 2.5. And then we have S squared plus 50. So if I do basically 0.4, 0.05, that's equal to 50. So that's how I got that 50. Oh, and then I need the S plus 3. Sorry, S plus 3. Okay, so we've been able to get the ILs of S. So kind of this is what I wrote on the previous slide, which is basically that ILs of S equals Vn over CLs of S plus CLs of S. I could have also use KVL to derive this equation. And then plugging in the numbers leads to this. Note that this is just 20 over S. It's just 0.05, 1 over 0.05 S. It's just a different way of writing it. And just like 0.4 is just really, 1 over 0.4 is just equal to 2.5. Okay, so now let's say we want to find ILs of t. So how do we do that? Well, we just need to find the inverse Laplace transform. So like I said, I'm going to multiply the top of bottom by S over 0.4 so that I get that this is just that ILs of S equals 2.5 S divided by S plus 3, S plus 50, which is really just equal. So now we can do a decomposition. So we're going to have A0 plus A1, S plus 3 plus A2, S plus J square root of 50 plus A3, S minus J the square root of 50. And at this point, we know A0 is 0 because this is third order in the denominator and the numerator is first order. And so we know that the order of the numerator is higher than the denominator, so we know that A0 will be 0. So I'm just going to remove it, and that's going to give me some extra space to rewrite this. So plus A3 S minus J square root of 50. So we're going to use our method to compute inverse Laplace transforms to get the inverse Laplace of this. So we're going to get that first. A1 equals 2.5 S divided by S squared plus 50 evaluated at S equals -3. So remember, you multiply this expression by S plus 3 and then evaluate at -3 to get the A1. And so we're going to get -3 squared is 9. So we have 59, and then 3 times 2.5, well, negative 3 times 2.5 is 7.5. So whatever that is, that would be the value. I think it's like 0.117 or something. I'm not even gonna look it up. It's on the next slide. Okay, and then A2, we do the same trick. So we're gonna have 2.5s divided by s plus 3, s minus j squared of 50, evaluated at s equals negative j squared of 50. So we're going to get negative j 2.5 square root of 50 divided by negative j square root of 50 plus 3 minus 2j square root of 50. And then you can plug this into your calculator and you're going to get a number. And then you can do the same thing to find A3. So on the next slide, I actually did the calculation, so I'm just going to go to that slide. Okay, so here for s equals negative 3, like I said, you take this expression, both sides of this expression, you multiply by s plus 3 and evaluate at negative 3, and then you can get what A1 is. Then you take both sides of the expression, of this expression, you multiply by s plus the square root of j squared of 50, and you evaluate at negative j squared of 50, and that's going to give you A2, which is this. Now remember that these are conjugates of each other. So when you evaluate A3, you can apply the same trick, but you better get the complex conjugate back. Additionally, the one with the s plus tells you what the 2 times this should be the cosine coefficient and 2 times this should be the sine coefficient. Okay, so now that we have all the coefficients, now we can actually take the inverse Laplace to get our answer. So let me just go ahead and do that. So what we found in the previous slide was this. So we can inverse Laplace this, so we're going to get negative 1.271 e to the negative 3t. We can inverse Laplace this, so 2 times this cosine, so 2 times this is this, sorry, 2 times this is this here, and then times cosine the square root of 50t, and then 2 times this is this times sine square root of 50t. So we just solved this LC circuit fairly easy while avoiding a lot of the hurdles that we had to go through when we did differential equations. So if you recollect, to solve this, you had to first find the particular response, which is essentially this, and then you had to match initial conditions to get your homogeneous solution, which is essentially this. Now we did everything in one step by simply finding the Laplace transform of the inductor current and then taking the inverse Laplace. So that's basically why we like Laplace transforms. They make solving these circuits with inductors and capacitors much easier, and as we will learn later, they also allow us to look at more generic properties of circuits. Okay, so in general, if you have something that looks like this, where the roots are 3 and some imaginary roots, remember that the cosine part, if you look at the one with the plus sign, the sine part will be the imaginary part of the coefficient, and the cosine part is the real part, and in both cases you have to multiply them by 2. Effectively, you're using Euler's identity, which says that cosine equals e to the j omega t plus e to the j omega t, and then so 2 cosine equals that, and 2 sine equals e to the j omega t minus e to the negative j omega t, and then there should be a j here. And so you're using this to inverse Laplace, but instead of writing it in this complex exponential form, you're writing things in a sine and cosine form. Okay, so let's do one more example and then we can go to the next part of the lecture where we actually include the initial conditions. So just to summarize, we can generalize the concept of resistances to what we call an impedance in the Laplace domain, and that will allow us to deal with resistors, capacitors, and inductors algebraically in the same way we did with resistors in the time domain. Additionally, we also, just like when we have resistances, we had this concept of the conductance, G. We can also have admittance in the Laplace domain. Impedance is related to resistance and admittance is related to this conductance. So we can also write what our admittance is, where the current is just V times Y, and we have that C equals 1 over Y and vice versa. So for a resistor, Y is just 1 over R. For a capacitor, Y is SC. And for an inductor, Y is 1 over S times L. So this is just some terminology. In general, you know, you should just use whatever's concept is most convenient for you. All right, so let's look at this particular circuit and let's find so it's saying to use impedances to find the equivalent circuits in the Laplace domain, and then determine VC sub S assuming 0 initial conditions. So our equivalent circuit, so U of t is just 1 over S. Remember, our resistor just becomes 10. That's the impedance of our resistor. For a capacitor, it would be 5S. Sorry, inductor. And then for the capacitor, it would be 1 over S, since it's 1 farad, so 1S. So if we want to find VC sub S, well, that's just going to be VC sub S is equal to I sub S. So it's going to be equal to 1 over S, which is the current coming in, times the equivalent resistance, which is just 10 in parallel with 5S in parallel with 1 over S. And so that's going to give us 1 over S. And I'm just going to put a money sign to kind of distinguish from the fact that these are S's and not 5s. 1 over 10 plus 1 over 5S plus 1 over, S to the negative 1. Additionally, we can multiply the bottom by S and the top by S. Yeah, so that we have basically 1 over S times 1 over 10. So this is what we have, 1 over S, 1 over 10 plus 1 over 5S plus S. And then we can say that this is just equal to 1 over S, or here, S squared plus S over 10 plus 1 over 5. And that's it. That's the solution for our circuit. So here's kind of written more nicely. So this is saying that I sub S equals the impedance, the equivalent impedance it's I sub s equals the VC divided by the impedance. So I did it slightly different here, and then I divided both sides by BC to get this. In the previous slide, I divided everything by 50, so what I actually got was just 1 over s squared plus s over 10 plus 1 over 5. But it's the same thing, you know, you just divide the top and bottom by 50. Okay, so yeah, so that's basically solving circuits using, or this, finding the zero state response, or the response when the initial conditions are 0. Now the next step will be to include initial conditions in the Laplace domain, and that's going to be the next half of the lecture. Okay, so blah, blah, blah. What else is there? For some reason I had more slides, but they're all just showing the same thing over and over again. Yep, they're all just showing the same thing over and over again. Okay, let's go through the next few slides.